Yeah. So dual correspondence, we will do it again, right? We already learned this before. We have a cat space, right? And then we have a bra space. So what do I mean? I have a vector, the corresponding is the bra. Right? That's why I say we keep repeating. And I hope you are very comfortable with this bracket now, right? Although we've gone with some very complicated equation, you still don't fully understand. But now you know you're okay with bracket, right? It's so familiar with this. So we also say that alpha times A corresponds to what in the dual space, in the bra space? Someone say, what's that? Someone say, alpha, I add alpha star bra A, yeah? Do you agree? No, you cannot agree to yourself. Do you agree? Or can I write this? Which is right, which is wrong, or both right, both wrong?
Both are right. It's just a scalar.
Both right. Yeah, alpha star scalar. If you are not sure, then just think about, what if I write it in the matrix form? It doesn't matter the scalar put on the left or right, right? It's the same, right? But these are very useful. You need to get used to this so that when you are dealing with this, it becomes so easy for you. You feel difficult just because it's very strange to you. You dare not to do anything when you see such a strange symbol, right? Combination. Okay, good. Okay, now, if I apply a matrix to a vector, what should I get? First of all, this is a matrix, right? Or operator. This is a vector, right? Overall, what is this? Overall, X, a matrix applied to the vector. Vector, right? So this is a vector. So is corresponding, the dual correspondence must be what? It should also be a bra vector, right? Of course, it is a bra vector. But is it equals to A? No, right? It is. He guessed it's X dagger. If you have no choice, you need to guess. Will you agree with his guess? Yeah, you think about star, right? But this is a matrix. So what is dagger? Transpose and complex conjugate. Very good, right? So does it make sense based on what you have learned? This is the transpose of this guy. This is the complex conjugate. So it looks like correct, right? Correspondence must be dagger. What if I say this? Because now I say this equal to this. Am I correct? Why?
Because two matrix multiplication.
Right. So first, but however, first of all, this is matrix. How about this? A.
Vector.
This is vector. Right? So it's not two matrix multiplication, right? But can you continue to explain why? If you just think in the matrix form.
That's a column.
Very good. So first of all, they are not equal, and not just not equal. This one is wrong, just wrong. Right? This is just wrong. Because all you need to do is just think about it. This is a, let's say, n by n matrix, but this is a 1 by n row. How do you do matrix multiplication? Row times column, this has n element, this is 1. This doesn't work. Right? So naturally, this one works because this one is row times n, right? So n times n. n times n, right? So this one works, right? So, but now, of course, to memorize, it's easy. Bra becomes cat, and then matrix becomes a matrix dagger. And you just need to swap it because you know that it's not going to work, right? So this is another correlation. Okay, and finally, just some equation. Just remember, we actually learned earlier. VW, what does it mean? What is this operation again? Inner product, right? So it is a what? Scalar, matrix, or vector? Scalar. So how are they related if I swap them? If you need to guess. Complex conjugate. Because it's a scalar, right? We proved that, but that's how I memorize it. Similarly, we did not prove it. We just take it for granted, right? We proved it in the previous, the other classes, but we don't have the time. How about we see if you understand what it means here? What does this mean? Just read from the left to right. A bra, a vector, multiply to a matrix, multiply to a vector. This is legitimate, right? Basically what I'm saying is this. A row vector times n by n, and then times a column vector. It works. We go through the multiplication, right? This guy will equals to, I decide to swap them. W, M, yeah, just now someone say scalar, right? Just now someone say, I don't know who said that. That's right, this is a scalar, right? If it's scalar, then how do I make these two the same? If I want to remember, right? First of all, outside, what is that? For a scalar, do you use dagger? Just complex conjugate, right? But is that all? What else will you guess? So actually, you can think of this. This one is just another vector. M times W is just another vector, U. Yeah, so yes, very good. So this one is just the U bra. So if it is U bra, what do we need to do? You need to add a dagger. Okay, so confusing, but hope that you can think about it. If you cannot, use this way to memorize it. That will be very helpful, okay? And we'll keep playing with this. Any questions? So, we go to another matrix, right? Non-stop. Unitary matrix is very, very important. All the quantum gates are unitary. Okay, because they are reversible. So let's recall. I already recalled, we just talked about this today. What is a Hermitian matrix? Right, you don't want to mess up with Hermitian matrix. What is that again? A equals to A dagger, very good. Where A dagger is just transpose times this, right? So what is a unitary matrix? A unitary matrix is, look at this, U, I just call it U, you call it A, that is okay, right? U, instead of U equal to U dagger, is U inverse equals to U dagger. That is the only difference. U inverse equals to U dagger. Right, so that's a way to memorize. Or equivalently, it means U times U dagger equals to U dagger times U equals to identity. Right? Basically, it's just saying that U inverse U dagger, I multiply U from left and U from right. Anything multiplied by its inverse is 1, right? That is the identity matrix. So you can think of this as definition for unitary matrix. Whenever people say unitary, that is the first thing you need to realize. That is the first thing. Is that okay? Now, we don't go to details, so I hope that you can read the book. I also uploaded some suggested exercise yesterday, right? Try to play. It's from my previous book. Just practice. But why unitary matrix is so important? Let's just look at an example. The conclusion is that because it preserves, it keeps the inner product of two vectors. So inner product is very important. You saw that we have been using it throughout the process. And that makes sense, right? Sometimes inner product, you can think it is just like in this space, this table, it has two edges with a corner of 90 degrees. And no matter how I transform the system, I rotate my room, I rotate the table 90 degrees, whatever, the corner between these two edges has to be unchanged. And that is the inner product, right? Because the angle determines the inner product of these two edges. And inner product has a lot of physical significance. The point is, when I see this physics happening, I hope that it's still happening, even I lie down or stand up or look from the top or look from the bottom. The same physics should happen, right? So that's why if I do any transformation, I hope the inner product will keep unchanged. For example, then let's think about an unitary transformation. I have two vectors, G. After a unitary matrix, it becomes UG equals to, let's say, G dash. I did something to rotate the system. And I have another vector F. Applying the same transformation, it gives me UF F dash. Transform. Don't know how to write today. Transform by U. Is this okay? The problem statement. I have two vectors in the original space, U and G and F. Now I do a transformation to both of them at the same time, or I transform the coordinate. Now they become F dash and G dash. Okay? So the inner product after transformation is what? How do you find the inner product after transformation? How do you write it? I don't ask you to calculate. How do you write it? In bracket notation.
So,
You write what? What times what? Huh? One is cat and one is bra. So what times what? What is on the left? Thank you. G prime bra times. Is this okay? That's the inner product. Okay. Then, however, what is F dash? I know that already. It's just UF, right? But what is G bra? We just learned it. What is that? Huh? G dash bra equal to G bra? U dash. Yeah, the correspondence, right? We just said. Because this one corresponds to this one. So because of this, then I can write this is G, U dagger, U, F. Make sense? Again, looks very difficult, but again, this is all multiplication. Bra times a matrix times a matrix times a cat. Row vector times a matrix times a column vector. I can do associative rule, right? So that's why I say if U is unitary, if it is unitary, what does it mean? U dagger U equals to what? Identity matrix. We just say that, right? This is definition. So then it means this one equals to G, I, F. Although I is identity, but it's still a matrix. But anything times a matrix equals to itself. Yeah? So this is equal to what? G inner product F. The original inner product. The inner product of the original vector before transformation. Right? So we show that G dash F dash inner product equal to G and F inner product. Right? So it preserves the inner product. That's the beauty of unitary matrix. And all quantum gates needs to be unitary. If you have an invention, a new gate you find so efficient, wow, save a lot of energy, very accurate, no error, but turn out not unitary, then you are sure that you are wrong. Right? Unless you have some new paradigm, new invention of a quantum computing method. Right? Otherwise, in the traditional framework, no such thing. Okay? So that is the unitary matrix. But I go through this because we really need to practice the bracket notation and be very familiar with that. That's why I want to spend all this time. Any questions? Okay, the last topic of this linear algebra preliminary is about the transformation matrix. I just talked about transformation. But now the point is this. Let's say, like the question is, I have an O basis. This O basis has the basis vector 0, 1, all the way to n minus 1. So what is this dimension? What is the dimension of this space? N, right? Because I have an n basis vector. Of course, I did not say that they are orthonormal, but we assume they are orthonormal already. N basis, linear independence from each other. In our real 3D, we just have 0, 1, 2, x hat, y hat, z hat. That's a special case, right? I can write it as this also, right? This is the symbol for the set, right? So I can just say this is I. Of course, I can go from 0 to n minus 1. And the simple one is, for example, it can be 0 and 1. This is a 2D space, right? 1 qubit. So fine. Then I say I want to represent it, right? So you use this to represent a vector. For example, here, I have this side is represented as a linear combination of 0 and 1. We learned that earlier, right? I want to represent it in a new basis, which is, it also has its basis, but I add the dash to it. It is still n-dimensional, but the name is just a label, now has a dash. Dash in this sense, right? But I can call it plus and minus. This is also a two-dimensional 1 qubit basis. One is 0, 1, one is plus minus. A fake example is like this. I want to use this 45 degree as the basis. Is this clear about the background? Right, so we have an O basis, just a coordinate, Originally, I used x, y, z as a coordinates to measure everything in this room. Later, I might want to use a spherical coordinates, right, to measure everything in this room. They are different bases. Okay? Now, if I already know how to represent a vector in the old basis, then how do I find its representation in the new basis? Then you can use this matrix to represent a vector in the new basis. What matrix is this? U equals to I dash inner product J. Wow, this is a very difficult symbol. Anyone can decipher what it means here? What it means here? I mean, I am talking about matrix, but I only write down one term. Do you understand what it means? Basically, how many elements do you have in a matrix? He said n by n. And that is right because we're doing a transformation between n bases to another n bases, right? So basically here is an n by n matrix. But I only write down 1 because this is talking about the value of ith row, jth column element. Now, do you understand? So, 0th row, 0th column is going to be 0 dash inner product with 0. Okay, so dash means the new basis. No, without dash is the old basis. Can be confusing. Don't worry yet. I will have an example. But in summary, is this. With this, then, any vector you will transform, if you try to represent it in the new basis, is U times this vector. So this is the old, this is the new representation. And then how about matrix? Matrix got to change also, right? It becomes U, M, U dagger. We are not proving it, but you need to memorize it, keep in cheat sheet. Basically, you need to know how to do that. Okay, so we'll do an example. Right now it's confusing, but the background is, again, we have a matrix originally represented in the old basis. For example, 3x hat plus. Let me write example here. For example, just in 3D example, you can be 3x hat plus 2y hat minus 1c hat, right? And then when you go to the new basis, I don't know, it might be 6x hat dash plus 4y hat dash minus 2c hat dash. Do you see what I'm talking about? And they are the same vector. So we have an O basis. You represent psi in terms of 1 and 0. Now I want to know, how about represent it as plus and minus? How do I write it? In order to do that, you use this matrix, right? I will explain again how to do it. And then your new representation is U times the original representation. For matrix, you go through this equation. Confusing, right? So let's do an example. Then you will understand what I mean. So let's say now I have my O basis, as I said, the so-called O basis, because I represent the vector in the 0 basis, right? So 0 is just the 0, right? I just based on what I wrote earlier, the O basis, I don't have a dash. So I call it 0 and 1, and it happened to be 0 and 1. Now I want to represent in the new basis, so it is 0 dash, right? But this is actually the plus, and this is 1 dash, which is equal to minus, right? It's just a name. It is just a name, so I can call it anything. But what I'm trying to say is just that old basis is 0 and 1, new basis is 0 dash and 1 dash. In this figure, the old is just 0 and 1, the new is plus and minus. Okay? So now, how do I construct the matrix? I can repeat what I said earlier. It is just equal to I dash J, right? The ith row, new I will be the row, and J will be the column. So now I spell it out. It is 2 by 2. Basically, it is 0 dash 0, 0 dash 1, right? Because this is a 0th row. So I have 0 dash, but 0th column, first column. This is 0th column, first column. Similarly, this is the first row, so I put 1 dash. And then this is 0th column, first row, first column. Right? So do you see that? The bra is always the new basis. The cat is the old basis. But which one to put is depending on the row. For the bra, you put the row, right? If it is row, the bra value determined by the row. 0, you have 0, 0, and then 1, 1. But for the cat, it's column 0, 0, 1, 1. We don't prove it. You can prove it, but the point is, this is very convenient. So I hope you can memorize this. But in this particular case, what is 0 dash? It's just plus, right? I say 0 dash, the new coordinates is plus, right? And then the O is still 0, plus 1, and then this is minus 0, minus 1. Any questions? So, what is the meaning of plus 0 here? This is what? What operation again? Inner product. You might get it from elsewhere, but for this particular picture, the inner product is what? Is this inner product with this, right? And what is the overlap? 1 over square root 2. Yeah, cosine 45. Okay, this one I won't prove to you. So all of them are 1 over square root 2, 1 over square root 2, 1 over square root 2. But the last one is negative 1 over square root 2. Because negative is here, and 1 is here. Their overlap angle is 135 degrees. Okay, because inner product is the magnitude times cosine angle. That's why you have this, right? Which is equals to 1 over square root 2, 1, 1, 1, negative 1. This happened to be like which gay? Hadama gay, yeah. But this is not the real representation, right? I mentioned many times. Remember, this is a fake, right? This is a fake qubit, right? So do not think that this is the qubit space, right? Make sure that you don't mess up. So for example, let's look at this. If I have states equals to alpha, beta, in the 0 and 1 basis means I have alpha part of 0 and beta part of 1. This one we mentioned many times already. Is this okay? Just a general state. How is it represented in the new basis? This is O basis. How do I do that in the new basis? Yes. So all I need to do just U times psi. Then this will give me the new basis representation. And what is that? That is 1 over square root 2, 1, 1, 1, negative 1 times alpha beta. You go through the math, it's just 1 over square root 2, alpha plus beta, alpha minus beta. And we've done that before. This is correct. You can compare to our exercise before. But now, what is this top? This part represents plus, and this part represents minus. All I'm trying to show you is that once you get this matrix, then you can do transformation of coordinates or rotation, representation of vector easily. This one you can use trigonometry to get it. We have done that before. But now you don't need trigonometry. The point is you need to know the inner product between these spaces. Then that you will get, even if it's a high dimensional one, you will get that. Okay. I know there's lots of math. How about let's take a rest for 1 minute? And that's it. I think I'm very slow. But yeah, I think it's necessary though.
Yeah, fine. So, solving eigenvectors, those are the ones that we
No. That is not really the component of the eigenvector. Actually, these are all the bases, and we are finding is how much overlap between the old basis and the new basis, and that becomes the element.
zero, one. So this would be like the component zero.
Not component, yes. The old basis 0, 1, yeah, but not eigenvalue of anything. Uh-huh. Okay, so you are trying to say it in some cases the basis they are the eigenvector of something, right? Because we try to diagonalize a basis, a matrix, and then the basis is their eigenvector. That's correct. But here we don't particularly say that it can apply to anything. Yeah, because we don't. When you talk about eigenvector, you need to have a corresponding matrix, right? But here we did not mention any matrix. My eigenvector must correspond to a matrix when you talk about eigenvector.
No, I get that, yeah, so that's your diagonal. That's a percent. To get this part right here, I think it's just the component of the old basis.
Yes, the basis vector of the old basis. Yeah, correct. Very good. This is a summary, right? You go back to take a look. We will talk about Ch3 today.